Hello, this is Gary LaRue, Technical Editor at Microwave Journal. It's my pleasure to welcome you to today's webinar discussing silicon technologies for 5GMillimeter wave phased array systems. The presentation will be given by Anirban Bandyopadhyay of GlobalFoundries. Before we begin his presentation, let me cover a few points about our agenda today. The webinar will last an hour. After the presentation, we'll have time for questions. You may submit a question during the presentation by typing it in the Q&A box, which you'll find on the right-hand side of the WebEx screen. Please make sure the setting shows all panelists, which is the default. After the webinar, you will receive a copy of the slides, and we're also recording this, so you can watch it again and recommend it to colleagues who aren't able to join us today. Now let me introduce our presenter, Anirban Bandyopadhyay. Anirban is a director in the GlobalFoundries Strategic Applications Organization. He focuses on hardware architecture, technology evaluation, and market studies for RF and millimeter wave applications. Previously, he managed a design enablement group for RF and wireless, and led a strategic applications and marketing studies at IBM Microelectronics before it became part of GlobalFoundries. He also worked at Intel, where he concentrated on silicon photonics and signal integrity and RF and mixed signal systems on a chip. Anirban received a PhD in electrical engineering at the Tata Institute of Fundamental Research in India, and he did postdoctoral research at Oregon State University. He's published articles in international journals, written a book chapter on optical photodetectors, and holds 5 U.S. patents. Anirban, I'll now turn the screen over to you.
Thanks, Gary. Thanks for the nice introduction, and thank you all for joining the webinar. The topic of my talk today is silicon technologies for 5G and millimeter wave phase array systems. As you all know, there is a lot of activities going on the millimeter wave applications. Millimeter wave has been around for quite some time, but there are a lot of drive towards more commercialized applications of millimeter wave. My talk will be focused today on how different silicon technologies play important role for building these phase array systems, particularly with emphasis to 5G. The outline of my talk would be, first I will start with phase array antenna systems and give a brief overview about the different beamforming schemes. That will set the tone for talking about different silicon technologies and how they play key roles in building these beamforming systems. And lastly, I will talk about some of the different architecture options that basically allow different technologies to play key role based on the chip partitioning and the different application requirement. So let's start with a brief overview of the phased array antenna system and different beamforming schemes. So when we talk about millimeter wave, there is a big difference between sub-6 GHz communication and millimeter wave, and that is using phase array antenna system. What phase array antenna system does, instead of using a single antenna, they use multiple antenna, and that they call array, and they try to do a constructive interference among the beams of different antennas while receiving as well transmitting. Now, what is special about it is this: by doing that, instead of doing a big kind of a broad beam, you basically focus the energy from each antenna into a particular direction. Depends on the antenna size, the frequency of the wave, and the number of elements of the array, the beam angle is determined. So how it is important for applications? So most of the applications for millimeter wave, they use phase array antenna systems. Today we are familiar with autoradar, they use for automotive collision detections. We also are familiar with the wireless backhaul, where this kind of systems have already been in place. But there are so many emerging applications coming in, starting with fixed wireless. So you guys must have heard about a lot of activity going on the millimeter wave fixed wireless. That is another example where these phased array systems will be used. 5G, both the UE devices, whether it's a handset or any other form factor kind of user equipments, or the infrastructure devices. It can be small cells, it can be micro, femto, pico cells, it can be a macro tower. So these phase systems will be used. And last but not the least, that satellite communication. We use beamforming in satellite communication today, but that is mostly for geosynchronous satellite systems. We are talking about some low Earth orbit satellite communications where huge number of these elements will be used to focus the beam towards the satellite and vice versa. And WiGig is of course very familiar to all of us. This has been around for quite some time. That also uses millimeter wave beamforming. Why I'm spending so much time on this is because this focusing beam using phase array allows us two things. It allows us spatial multiplexing. We'll talk about that in the next slide. Also, it allows the power level transmitted by each antenna element to be reduced drastically. And the reduction is happening because we are concentrating all the energy in one direction instead of broadcasting with a big kind of a beam with a wide angle, just like we do in a sub-6 GHz studio. Why it is relevant? Since the transmitter power for each antenna is reduced, now instead of 3-5 semiconductors, we can use silicon technologies. As you all know, that high power, high frequency usage is kind of a domain of 3-5 materials, whether it's a gallium arsenide, indium phosphide, gallium nitride, those kinds of materials. The reason silicon technologies normally are not considered is because of the fact it can't produce the kind of power that is needed. But when you use a phase array system, since the transmitter power requirement reduced, because each transmitter power is now kind of interfered in the constructive direction to concentrate the power, the requirement for each power amplifier connected with each antenna is reduced. And that's where silicon technology come into picture. Let's talk about how spatial multiplexing also helps us. And that's with respect to the special focus on 5G millimeter wave. Now, 5G, we have been hearing, there is a lot of hype around us. There are a lot of webinars, conferences, talks going on. There are a lot of research going on as we are speaking. The big difference, if you think about from the antenna point of view, today we are using antennas which are big just because we are mostly sub-6 GHz. But another reason it is also different is the beam that is broadcasting, it is not particularly focused toward one user. So multiple users use the same beam from the same antenna, as I am showing it in the left-hand side here. When you go to 5G, the thing changes. The big difference here is since the wavelength is so small, the antenna dimension becomes smaller. So now we can put a lot of antenna elements. We can do that in sub-6 GHz also, and we are doing it today in massive MIMO installations of 4G, LTE Pro, and going towards sub-6 GHz 5G. But the dimensions are bigger. So when you are talking about millimeter wave, particularly 24 to 40 GHz, which basically we are thinking of the first generation of millimeter wave 5G, what we'll see here, the antenna dimension shrinks, the array size becomes bigger, because now we can accommodate more arrays within the same form factor, and that gives rise to multiple beams, and each beam is targeted towards, ideally, one user. How it helps? Basically, it eliminates a lot of interference from other sides. So the beam can only intercept undesired signals along its path, which is within that narrow angle. So that tremendously enhances the signal to interference ratio. That's the reason it is so important. Let me go to the next slide to talk about different beamforming schemes. We talked about different beamforming. We talked about how beamforming helps us, but there are different ways of doing beamforming. There are three different schemes. One is analog, one is digital/baseband, and the third one is the hybrid beamforming. The analog beamforming, that's basically on the top. What it does, let's say there is 4 antennas. By the way, for any phase array system, the ideal separation between the antenna elements are λ/2, where lambda is the wavelength of the operation. Now, the number of antennas can be 4, 8, or even bigger. What I'm showing here is from each antenna, there is a path. there is a transmitter path through power amplifier and a receive path through LNA, low noise amplifier. In case of an analog beamforming, what they do, they basically control the phase and amplitude of each wave to be transmitted or received through each antenna at the analog domain. By doing that, what they do, they can now combine or split the beam. In case of reception, they combine the beams. In case of transmitter, they split the beam at this point. The rest of the system is just like the conventional system that we know today. There is up-down conversion, data converter, and then it's all logic after that. In case of digital baseband beamforming, the difference is they don't do the phase amplitude control at this stage. So this is the front-end module part of it, the switch, LNA, PA. But what they do the traditional up-down conversion without doing any manipulation to the phase and amplitude. They do the data conversion to transfer into the baseband domain, that means the digital domain, and then they do the phase shifting. The big difference between these two are that all the digital phase shifting is happening where it's analog, but then it's all happening after the ADC-DAC. And it's very important for us to remember that. In case of hybrid, normally it is used for a large array. When the array becomes large, like a lot of small cells, a lot of satellite communications, backhaul kind of applications, the array size can be 256, it can be 1,000 or even bigger than that. In that case, we do something which is a mix and match of both. So you can see we also manipulate the phase and amplitude here like analog beamforming, but at the same time, we also do digital phase shifting like a digital beamforming. That way, we don't have to manipulation of phase and amplitude for many arrays. That's the way we bifurcate. But then there is another issue that I want to highlight here. The main difference between analog and digital, not just the operation mechanism, so far that system requirement is concerned, is analog beamforming is the lowest power dissipation mechanism. Because as you can see, the maximum power dissipation happens in the AD converters, in the PLLs, and of course in the PAs as well. PAs, there is no refrain. You have to have as many PAs unless you do some kind of a, sometimes people do multiple user using the same PA, but otherwise there is no difference there. The difference comes in between ADC, DAC, and PLLs. So there, it's the lowest power dissipation because the number of those components are minimal. In case of baseband beamforming, there will be as many ADC, DAC as the number of antenna elements. So the power dissipation is very high. But the advantage of digital beamforming is the flexibility. When you do beam steering, when you do multi-user, this is the preferred mechanism for that. Hybrid actually has both. So it has the simplicity, kind of compromisation or optimization of the power dissipation, and at the same time the flexibility of it. The reason I'm spending time on this architecture, because a lot of the figure of merits will follow from which system you adopt ultimately. We'll talk about that when silicon technology will come into picture. Before going to silicon technology, I'd like to show a real-life example of a product using hybrid beamforming. This is a product from Anokiwave. They have done a 26.5 to 29.5 gigahertz. It's a hybrid beamformer chip. Each chip support 4 antennas. You see the board here. On this side, the chips are. On the flip side, you will see the antennas. So each chip basically addresses 4 elements of the antennas. In this system, we are showing 64. So basically, they are doing a hybrid beamforming with all the switches, LNAs, PAs, phase and amplitude controllers are there. I just wanted to show a real-life example because it's a big difference between a product and actual schematics. We'll go to some of the figure of merits later. So let's keep to the next section. So the next section will talk about silicon technologies. Different silicon technologies are there which can play an important role in phase array systems. We'll talk about those things. So to start the discussion of silicon technology, I thought the better way it would be how to differentiate one technology with another in terms of performance. So I am showing here 2 plots, one for the receiver, one for the transmitter. The receiver plot, I am plotting G by T, which is the antenna gain divided by antenna temperature, as a function of number of antenna elements. Don't get scared by the numbers. Actually, in some of the systems like satellite communication, a number of radiating elements can be as big as this. But the point is not that. The point is when you plot antenna gain or versus the radiating elements as a function of noise figure of the receivers, you will see if some technology can offer improved noise figure, like if you go from 2.5 to 1.5, as this arrow suggests, what happens, the number of array elements you need is reduced. So it also basically reduces not only the form factor, the overall the system cost as well. And also it is not very easy to deal with a big, large systems because routing in millimeter wave is a very, very critical thing, and we'll talk about that. Let's come to the transmitter power. The same scenario, if you plot the EIRP, by EIRP we mean the effective isotropic radiated power, and again versus the number of array elements. Now, if we consider different technologies, we have plotted it for different transmitter power. So if we go from 20 to 50 milliwatt, let's say I have another technology which can basically transmit 50 milliwatt per element, then effectively I need, for the same EIRP specs that I have for my application, I need less number of elements. So basically both help me from the receiver and transmitter side to reduce the system size, form factor, and overall cost. So I just wanted to highlight that because that's the moot point behind why there is a differentiation of technologies needed. We'll go to more details about layouts and other applications later. So let's talk about different technologies that we are thinking about today. So we'll be considering today bulk CMOS technology. I call it RF CMOS. Now, I'm also showing in the parentheses the nodes. That doesn't mean everybody has to confine themselves to 65 to 20 nanometer. There are systems can be built with 90 nanometer or even below 20 nanometer as well. But these are the most widely popular systems reported. That's the reason I'm talking about it here. So for RF CMOS, the biggest advantage is this is the main technology of choice for sub-6 GHz transceiver. So there are a lot of common IPs that's available that can be reused for the millimeter wave transceiver as well. Number one. Number two, there is a huge supply base for this because there are so many foundries that offer that. That's the big advantage of it. And there are some tractions in some of the applications. These are mostly low power applications like YG, some of the auto radar like rear or side auto radar where the coverage distance is very small. You don't need to have too much transmitter power. For those applications, it can be considered. Let's come to SOI. So there are two kinds of SOI technology we'll talk about today. One is the partially depleted silicon and insulator, and the other one is the fully depleted silicon and insulator. I don't know how clearly you can see the picture. The big difference between bulk and SOI is the substrate is different. So in a SOI substrate, there is a silicon on insulator or silicon oxide layer. We call it buried oxide layer or box on top of the silicon substrate. And then we build the silicon devices on top of it. In a partially a PDSOI or partially depleted SOI technology, that silicon that is on top of the box is very thin. Actually thicker, sorry, and that's the reason for all operations regime on voltages, it's partially depleted. So for the FETs are concerned. In case of a fully depleted SOI, for all operations, it is fully depleted of charge carriers because the silicon film on top of the box is very thin. But that's the fundamental difference. What follows is SOI differentiates itself from bulk by having much lower parasitics. Like the junction capacitance, source and drain capacitance of FET is much lower. It also allows very easy device isolation by a shallow trench going to the box. It isolates one device from another. And you can do stacking, particularly for PDSOI. The thick box allows very efficient stacking, and we'll talk about that. What I want to mention here is the reason I put 45 SOI, because this is the current technology where a lot of results have been reported in the literature, and some products are already in the market. And this 45 SOI came from a technology which was already proven in ASICs and server domain. So this is a proven technology base. We are basically considering this for millimeter wave applications. But PDSOI, we have been using for 180 nanometer PDSOI for sub-6 GHz for cellular Wi-Fi front-end module today. We'll talk about that in more detail in terms of millimeter wave. In case of FDSOI or fully depleted SOI, the unique advantage it offers because of the thin box layer is that you can put another back bias from the back side of the box, and you can control the threshold voltage. What it allows is basically make the threshold voltage lower or higher to make it performance boost, as well as you can make the leakage reduction, depends on which direction you want to go. We'll talk about that as well. That has some unique implication in terms of applications. And last but not the least, we'll also talk about silicon germanium. So this is a BiCMOS technology where it differentiates itself from FET, that the main devices that you use for high performance is a bipolar transistor. It's a heterojunction bipolar transistor. And this technology, again, I am putting 130 to 90 nanometer. It doesn't have to be confined to that, but that is the technology being offered today. And it can be used for high-powered millimeter wave applications. We'll talk about that as well. Let's talk about some of the key figure of merits. With respect to that, we'll consider these technologies and compare them. So this is not an exhaustive list, but I'm just mentioning some of the key metrics here. Let's start with FTF max. FTF max basically refers to the maximum frequency where you have unity gain. In terms of FT, it is current voltage gain. For F max, it is the power gain. F max is very important because higher the F max will allow you to get higher P out or output power of a power amplifier. Now, there are so many parameters on the technology side that determines this. So the technology has to have high transconductance for the FET. The gate resistance has to be low for a high F max. The parasitic capacitance, like the overlap capacitance of CDG, is very important for F max. And also the back-end parasitics is also very important. But another important parameter is FT-GM over I, which is basically product of FT and the gain efficiency. Why it is important? So you can have a high self-gain technology. You can also have a high FT, but it's very important you have to operate at as much low bias current as possible for your power efficiency. And that's the reason these metrics are coming into picture. Going forward, back-end parasitics. Back-end is very important in millimeter wave because the parasitics at high frequency is very, very critical for your system design. Now, for a low back-end loss, your interconnect loss, your matching network loss will be improved. As a result, your PA power efficiency will be very good, and also you will get a very good noise figure of LNA. And that's the reason it's important. We'll talk about some of the technology which has been optimized with respect to this figure of merit. Transistor stacking. This is important because for some applications or components, the voltage swing as a result of the RF signal is still not very small. It doesn't scale. So basically, if you think that if you go to the lower node scaling of CMOS, the voltage scaling will be there, but then you have to still withstand the fluctuation of the voltages as a result of the RF signal. So the way to do that is stacking those FET devices. And that's basically done in a SOI in a very seamless way. So that's the reason transistor stacking is very important. So the technology with a higher breakdown voltage of the FET, which can isolate those FETs, is very important. Last but not the least, the flicker noise. So we are talking about system with a very low phase noise. When we talk about PLL, it is driven by a VCO, or voltage control oscillator. Its phase noise is very important. And that's the reason flicker noise play a very important role in millimeter wave systems. And the technology having a low flicker noise is definitely preferred for those applications. Let's go forward, talk about each technology separately. So let's talk about 45 SOI first. This technology has a very high FTF max, 290 gigahertz and 380 gigahertz F max. 290 gigahertz FT and 380 gigahertz F max that we have measured in global foundries. The important thing about this technology is, as I said, that SOI allows lower junction capacitance. It also allows high linearity. Both are very important for millimeter wave and in general RF applications. Also the low loss of the back end. We'll talk about in the next slide. This technology is being considered in many applications. People have already made product for 5G infrastructure, millimeter wave backhaul, satellite communications, and also it can be considered for a very high data rate photonics as well. What are the attractive features of this technology? So two key features of this technology is the substrate and the back end of the line optimization. So you can see in this curve, I am plotting the interconnect loss between two different substrates. One is high resistivity substrates, one is low resistivity substrates. You can see around 30 gigahertz, there is a 0.8 dB difference, which is huge in millimeter wave systems. How we are achieving that? we are doing a trap-rich substrate to increase artificially the resistivity of the substrate. And that helps. It helps not only the back end of the loss, it also improves the noise figure of the LNA. We'll talk about that. The other important thing on this technology is how the back end of the line is optimized. If you look into this picture, when we are simplifying the back end with a less number of metals, we are making sure that the height of the top metals where interconnections will be run is at a higher distance from the silicon, because where the loss coming into picture. So by optimizing the distance, lesser number of metals, thicker metals where the interconnections will be made, and all the key passive devices like inductors, transformers, MEMS will be made, we're making sure the back-end parasitics at a minimum. And we'll show that how it helps in some of the component performances. Let's talk about power amplifier. So this is an example of an internal benchmark circuit done by global foundry engineers. This is no way it is the most optimized device, but just to showcase you the power of this technology and where it comes from. So there are two designs I'm showing here. One is a single-ended PA. It's a 3-stack single-ended PA, and it has shown measured 20 dBm of PSAT at 28 gigahertz. The maximum efficiency as PSAT is around 30%. We also have a differential design where we can reach up to 23 dBm, which is double the power of the single-ended one. The maximum P is around 22%. The gain you can see from here is very good, is around 8 dB or so. But important thing to understand is how we are achieving that. Basically, what helps us is the capability of FET stacking. So in both the cases, we are doing 3 stacking. We can do more than that, but that's the advantage of this PDSOI technology. That is one thing, because then you don't have to have very high impedance ratio for your impedance matching for the input and output. So that's a very important point. Number two is, important thing is that the high PAE that we are getting, because the losses in the matching networks is also very important in determining the PA efficiency, and we can optimize that because of that. Now, further optimization of the design can probably take us further in both PSAT, gain, and PAE, but that's not the purpose here to talk about. The most important thing to talk about the technology FOMs, how it is affecting the component performance. Let's talk about switch here. So this is a K-band SPDT switch. By K-band, we mean 24 to 40 gigahertz. So this one has been designed with a single pole dual throw switches. It's a 3-stack NFET based switch on 45 SOI. The important parameter for a switch is insertion loss, isolation, linearity. But also it's very important the breakdown voltage of each FET, because you have to stack those FETs. And since the stacking is very important and 45 SOI or PDSOI allows this kind of stacking, we could stack 3 stack devices here. We can do more. But with that, we can achieve around 0.8 dB of insertion loss at 30 gigahertz. The isolation for this device is around 23-25 dB, but it can be improved further. It also shows very good linearity. Important thing to also show here is not that the parameters, linearity is extremely good. P1 dB is around 30 dBm, and output intermodulation, third order intermodulation IP3 is around 46 dBm for the two-tone measurements. But the important thing is also the model hardware correlation. It's a very important topic. I will come at the very end of my talk. That is not the raw performance of the technology. The PDK enablement and the quality of the PDK is extremely important for the component designers. And that's much more for millimeter wave compared to sub-6 gigahertz, but in general it is true. Let's go to some LNA performance. So there is a cascaded LNA single stage, and there for a 28 gigahertz, it's possible to achieve 1.9 dB of noise figure. The gain is around 11 dB at 28 gigahertz. It's a single stage. But the important thing is also understand this is also possible because the PDK is so good that the model hardware correlation shows that excellent fit here at different voltages. So the low noise figure, the low NF mean of the devices definitely helps. The low back-end losses definitely also help to achieve the low noise figure here, but it's also important for designers to have a very good model hardware correlation between PDK and the hardware. Let's change gear and talk about another technology. 22FDX. This is 22 nanometer FD-SOI technology offered by GlobalFoundries. The uniqueness of this technology is being optimized for millimeter wave SoC. The important thing is, since it is 22 nanometer, it has all the good features of the power performance scaling of CMOS node migration, low power, high density logic integration. But as I mentioned before, the fact that it's a thin box, you can basically do a back biasing here by a separate electrode. And by doing that, you can either shift the VT such a way, which is called forward bias for a performance boost, or you can also shift the VT such a way that the leakage is reduced. So for low standby power applications, it can be used by tweaking, and we can do that at the post-processing level because all you have to do is the bias there, the circuits. So this technology is being prepared for millimeter wave SoC, but it's also important to understand it's a low power millimeter wave application, and that's very important for us to understand. Some of the characteristics of this 22FDX, it has a very good FT Fmax, 350 FT and 325 gigahertz Fmax. The PFET also shows very good performance. The gain efficiency is excellent, and also the very low 1/f or flicker noise here. All these good characteristics making it a very good candidate for millimeter wave. I'm showing the figure of merit here, FT GM/I that I talked about. It shows that high FT GM/I also allows you to bias the PA or LNA at a lower bias current. It's very important to understand that. And the low flicker noise also allows you to have a low jitter PL. Let's shift focus to silicon germanium technology. So silicon germanium has been around for a long time. It has been one of the mainstay technology along with 3.5 for high power, high frequency applications. The important thing here to understand that the scaling here or the performance scaling happens here by vertical dimensions, mainly by the thickness of the base region. But when we do that, nothing comes free, the breakdown voltage reduces. So this curve shows the two kinds of breakdown voltage, BVCBO and BVCEO. So for BVCBO, you can see that as we try to push the technology to higher performance, the breakdown voltage reduces. But there is a demonstration showing that there is a 4-volt BVCBO with a FT more than 500 gigahertz, which shows the capability of silicon germanium platform. Not that we need all the time. We have to optimize, depends on what kind of voltage we need, what kind of FT, BV margin we need. But it's a possibility. The important thing is, by using this technology, you can avoid multi-stacking. That normally CMOS technologies have to do that. And that's a big thing, and that improves the PAE of the power amplifier. Let's talk about some of them. So here I'm showing some 130 nanometer and 90 nanometer BiCMOS technology offered by GlobalFoundries. And it shows the FT Fmax curve as a function of current density. And it also shows the maximum gain measured at different frequencies. You can see here, the nicety of this technology is it can really generate high Fmax. The 8XP, for example, crosses 350 gigahertz. If you go to 90 nanometer, you can go to even 370 even further with further optimization. Also important thing to note, you can get a very good high gain at a lower current. And that's the important thing about BiCMOS technology. Using HBT, you can reduce the current drive and you can basically get very good gain and performance. Let's see some of the components here. So this is one of the wideband PA reported from Professor Wang from Georgia Institute of Technology. What he's planning to do here is, so people can achieve high efficiency at PSAT, right? But what they lose is the linearity. So Doherty amplifier is one of the configurations where basically you balance between efficiency and linearity. But the problem with Doherty is it's a narrow band, right? By the nature of it, because you have to use the lambda by 4 phase shift to do that. So this technology basically allows to do a wideband Doherty PA, and which basically cover 28 to 39 gigahertz. And it's possible to achieve 17 dBm, even with this kind of optimizations. The good thing about it, you see this efficiency, right? So the normal class B, it basically shows the drastic reduction of efficiency as you come away from the PSAT. Here you can maintain the high efficiency even if the backoff is around 6 dB. And that's the whole purpose of this design here. But it also talk about that the efficiency of this technology as well. Let's talk about some of the other parameters. The power gain. PAE, for example. So it's possible to get around 28% of collector efficiency using silicon germanium technology here. It is 8x speed. And as I said, that even at the back off, you have a very good efficiency and very good power gain as well. That shows the power of the technology here. I also want to highlight a system features. So people talk about components, but what about the whole phase array system? So there is a demonstration by IBM and Ericsson, kind of a joint development. It has been announced a couple of years back in Mobile World Congress. So what they have done, they have used GlobalFoundries 130 nanometer silicon germanium technology to make the beamforming IC combined with the transceiver in a big chip. You can see the chip here. It's a huge chip, but it can basically generate 54 dBm of EIRP. Probably it can be pushed further. But the point is it's a 64 dual polarized antenna array, because I wanted to give a system a picture here of a real product based on the introduction that I have done. The important thing to realize here is that this system consists of lot of elements and lot of components. The plot here shows ideally as you increase the number of elements, EIRP should go by 20 log n. N is the number of elements. What's happening here is we are going very close to the theoretical limit. That shows the efficiency of that system, and they have achieved it using HPCG. I want to also talk about a minute about the bulk technologies as well. As I referred to, this is a technology, it's a low-cost technology. It has a wide kind of a supply chain and a lot of IPs availability. So why don't we use that? So I'm showing here the 40 nanometer technology from GlobalFoundries. It has a very good FTF max, more than 250 gigahertz, very good flicker noise, and high cap density. And it has PDK well developed with a very good hardware correlation. And it can be definitely considered for low power millimeter wave applications like side and rear radar for auto collisions and detections. And it can be also considered for YGIG applications as well. Let's go to the last part of my presentation. That is the architectures options, chip partitioning, and how it affects different silicon technology choice selections. Let's talk about a real-life layout of a beamforming system. So here, what I'm showing here is there is a quad array. There is two of them. There will be actually multiple of them. And then there is a beamformer chip at the center. The reason I have to show you here is in a 2D array like this, what you do, you receive the signal or transmit the signal through these antenna elements, through the PAs and LNAs within this chip. But then this millimeter wave has to come to the transceiver where the up-down conversion happens. Basically, it down converted to an IF frequencies, depends on which IF frequency, intermediate frequency you choose. And then subsequently it goes to the baseband. The problem of this layout is the following. There's a long interconnections. So if you do the up-down conversion here, you have to basically transmit the millimeter wave through a distance, depends on your form factor of the application. It can be several centimeters. It can be up to 10 centimeters, even longer. Depends on how big is the system. The millimeter wave system has the bad part of it is the loss. Even on a board, the best board you can get, the loss is very high, like 0.1 dB per millimeter. Now you can guess, even if for a 1 centimeter, you have a 1 dB kind of a loss. If the length is more, the loss will be even more. So what you normally do, you convert it to IF within here itself. And then you transmit the IF signal here. IF signal loss is much, much less compared to millimeter wave. Why I'm saying that? Because now you're talking about not only switch, PA, LNA, you're also talking about up-down converter as well. Now, if you wanted to do everything in a single chip, which you ideally wanted to do for lowest form factor and also the system cost point of view, the important thing is your back end of the loss has to be very low. Because there is some interconnection going on over silicon. The loss over silicon is much more than over a board. So you have to make sure the silicon technology is optimized for your back end of the loss. And that's the reason I'm showing it here. So this is a classic example of showing that you can miniaturize your system. You can put up-down converter also here, provided your back end of the loss is optimized here. Let's go to some of the architecture examples here. So one example I have to show here is the UE on the user equipment side. This is the complete SoC I'm showing in here, starting with the antenna. There is a beamformer. So it depends on what kind of beamformer you can use. You can have a digital phase shifter. In this case, I'm showing an example of a digital beamforming, but it can be analog as well, as I showed before. So the system can be partitioned into a beamforming chip. It can be a transceiver chip. And then the rest of them will be kind of logic, right, with a modem application processor come into picture. Now, let's see what are the different chip partitioning allows for using different semiconductor technologies. So I'm giving some examples here, not necessarily comprehensive, but let's say if somebody was to use 45SOI technology for this particular architecture. You can do the entire beamformer, excellent switch, excellent PA and LNA you can do. And then you can also integrate the up-down converter. As I was showing in the previous chart, that's the right thing to do for a system to reduce the loss of a long interconnection from transceiver chip to a beamformer chip. You can definitely do that integrated in a 45SOI. In a 22FD-SOI, you can do much more than that. Since it's a 22 nanometer SoC optimized technology, you can integrate the data converters and the digital phase shifters modem DSP as well. Now, the partitioning between this 45 and 22 FD-SOI, or the choice between these two, is entirely determined by what kind of RF power you want to generate. If you want to generate 20 dBm or more kind of a power, definitely 45SOI you can use it. 22 FD-SOI is probably useful for 20 dBm or less. But again, because of the phase array, you have plenty of applications where you don't need PA power output to be more than 20 dBm. So that is where you can use the advantage of SoC of 22FDX. The FinFET technology and the 12 nanometer FD-SOI technology is much more optimized for logic, analog mixed signals here. You get the power performance and the area scaling by using that. So if somebody asks me how you do the chip partitioning, it depends on the applications, the power level. I have a lot of choices here, so for the technologies available. Let's go to some different applications, like infrastructure, for example. So in an infrastructure, the number of arrays will be much more, like a small cell, backhaul, satellite communication, for example. So there they use a hybrid beamforming. I'm showing hybrid beamforming here. The analog and digital both are basically present here. The partitioning will be slightly different. Now the power level has to be higher, unless you have to use huge number of arrays, which basically system cost and the form factor doesn't allow. That's where silicon germanium comes into play. I showed you a complete system of silicon germanium integrated, but it can be definitely used for hybrid system as well in association with other technologies. For example, we can use the PA and LNA using silicon germanium and rest of the components of the beamforming chip using 45SOI. Another example of 45SOI is depends on the power level. If the power level power amplifier is not very high, we can integrate the whole thing in 45SOI for some applications, even for infrastructures. In case of 22FDX, mostly it will be integration of data converters, up-down converters, and also if it's the analog phase shifting, maybe some of the phase shifting part of it. The PA-LNA switch will be limited by what kind of EIRP and the array size you want, because the PA power output will be determined by that. So that's where we can extend this up to that, depends on the applications, but it all entirely depends on the system design choice and also the specs. And as we talked about before, in this part is mostly analog mixed signal and logic centric. That is where the bleeding edge CMOS like FinFET 14.7 nanometer, 12 nanometer FD-SOI comes into picture for digital FE and network processors kind of applications here. So the point here is there is no one size fit all. Depends on the specs, number of arrays, the amount of power you have to generate, and the EIRP. You have plenty of choices for different technologies. You can mix and match among them. That's the message I want to leave with you here. This is the last slide I have, and this is a very important topic. It's not just the raw performance of the technology. The important thing for a designer is that it has to have a good technology, which is characterized by all the FEMs, all the FEMs I talked about, like FTF Max, the different figure of merits. You need to have a very good back-end loss, as I talked about in different applications. But more important than that is also the PDK quality, the model hardware correlation. And that's the reason for different components I showed how the model hurdle correlations is good or bad, because that basically is very important for a fabless design company. Basically, that's the way they design it. And to reduce the number of iterations, it's very important that your PDK matches to the hardware as much as possible. Now, this is not a very easy statement to make, because the parasitics is really, really critical for millimeter wave as you go to high frequencies. So DRC LVS parasitic extraction is extremely important. So that allows us, so people run a lot of EM simulations to basically make sure in a millimeter wave domain how the interconnection, phase shifting, all the parasitics is working and meeting the specs or not. But it takes a lot of time. With a good PDK quality and design enablement with a lot of parasitics inbuilt into that, we basically help not only the improvement of the time of the design, at the same time, it also reduces the iteration cycle. That's the reason it's so important for us. This is the summary slide. So I talked about the overview of the millimeter wave phase array systems, different beamforming schemes, and also the pros and cons of each of the system when it is utilized. And it also basically allows us to use silicon technologies, because the power output from each of the transmitter is much lower now thanks to the phase array system. And that allows silicon technology to come into picture. In case of SOI, the biggest advantage for both partially and fully depleted is the junction capacitance. It also allows to define a technology for stacking and also device isolations. And the high FT/Fmax that you can reach can definitely allow us to build system for even the high frequency millimeter wave going beyond the Ka band as well. The important thing to understand is that there are technologies, depends on applications, where current handling is very important, breakdown voltage is important, and power output is extremely important for a high efficiency. BiCMOS technology is particularly geared for that applications. It also produces very low noise receiver as well. So there are options available for all of them. And then there is a low cost integration available using bulk CMOS as well. It entirely depends on the architecture, the application specs, and how a company wants to do chip partitioning. But there are a lot of technologies available from global foundries to address each of the applications and as the specs demands. Thank you all.
Thank you, Anirban. That was an excellent and very informative presentation. You kind of brought us up to speed on the capabilities of the various silicon processes, particularly as they can apply to 5G millimeter wave systems. We do have time for questions, so I would encourage our audience, if you have a question that you would like to ask, feel free to type it in on the right-hand side of your screen in the Q&A box, and we'll try to get to as many of your questions as possible. Let's start with one of the questions. One of our viewers is asking, how do you analyze the nonlinear power amplifier performance on beam patterns?
That's a very good point. Yes. So nonlinearity is definitely a key parameter, but you have to also understand that when you use the technology, you basically find out what is the actual power output. So if you use the technology with a higher PSAT, you can back off even more to get to the power output that you desire, and that will improve your linearity. And that's exactly where the high PSAT is very important to be addressed. So as I showed some examples here, for example, if somebody uses 45 RFSOI technology, you can get a PSAT of 23 dBm using a differential topology, for example. Now, let's say your application demands your power output has to be, let's say, 17 dB. So you can easily have a backup of 6 dB. So the kind of linearity you will get at the 6 dB is much more than if the backup is 3 dB. Now, let's say your technology has much more PSAT. You can back up even further, and your linearity will be further improved, where silicon germanium comes into picture. So that's the way you address nonlinearity, by choosing a correct technology with a high PSAT, and you back off to your desired power level.
Okay, a second question. What is the difference between technologies with different gate lengths, for example, 65 versus 28 nanometer? Does it impact the RF performance for the PA, or is the improvement only really in the digital side?
Excellent question. Yes, it does impact. As I showed, that different technology FOMs, FT/Fmax is a very important parameter, but this is not the only thing. But let's talk about FT/Fmax first. If you do the technology in a proper way for RF millimeter wave purpose, as you scale, your FT increases. That's because of the two reasons. Your scaling helps, your mobility helps your GM, so FT increases. But that doesn't mean that Fmax will also increase accordingly. So when you go somebody from 65 to 28, we know it's easier to increase the FT, but Fmax is not that easy. For that, you have to do a lot of things. The back end of the parasitics, the gate resistance come into picture. If you can do that, if you can also increase the Fmax, then definitely 20 nanometer can have higher FT and Fmax compared to 65 as well. Logic, of course, the power performance scaling is much better for 28. That's no brainer. But even for RF technology, you can make a FT Fmax if you properly optimize the technology, not just use the current digital 28 logic technology for this purpose. No, then you can only get the effect of logic scaling. You won't get the RF millimeter wave performance. You have to optimize the technology properly to address the gate resistance, back end of the parasitics. Then along with FT, you can increase the Fmax. Then it can be considered as superior compared to 65.
Okay. Can you comment on the millimeter wave switch technology? Is SOI still the preferred process?
Absolutely. So it's a good question in the sense because a lot of people think switch is probably not as much important in millimeter wave system as in sub-6 gigahertz. It's very challenging to do a high power switch in below 6 gigahertz, and that is mainly done by partially depleted SOI, 180 nanometer, 130 nanometer kind of node. But when it comes to millimeter wave, it's very important you have to isolate the transmitter with the receiver. And that isolation is a function of parasitics, particularly the C-off of the switch. Now, at millimeter wave frequency, C-off deteriorates. So we have to make sure the intrinsic DC C-off or C-off measured at DC is very, very low so that even at millimeter wave frequency, you get some isolation that you desire for your system. That's the isolation part of it. Next is the loss. Millimeter wave system in general is a very inefficient system. Why? Because it's very difficult to generate power in a transmitter at a high frequency. So in order to maintain as much power you can generate and feed it to your antenna feed, you have to make sure between PA and the antenna, minimum loss, and switch comes there. If you have a lousy switch, your insertion loss will be high, then you have to generate more power in your PA. That may not be possible in some technologies. And that's the reason good switch performance, both insertion loss and isolation is very important. But not the least, linearity is also important as well. Because when the power level is high, you have to make sure the switch behaves linearly. And that's why we believe that high resistivity substrate that PDSOI uses also helps us. So switch performance in millimeter wave is extremely important as well.
And a part B to the question from the same viewer is asking about the filter requirements for the millimeter wave bands and if there's filtering that can be done on chip or it really needs to be done off chip.
You know, it's an excellent question. We have been discussing about this in different forums. So let me give you a straight answer at this point. Lot of millimeter wave system. So let's step back a little bit. Why we use a hybrid filter today, the acoustic filters for sub-6 gigahertz? Because of band partitioning. The bands are very fragmented, but the way they are separated, they're very close to each other. So you have to make sure you have a very nice filter characteristics with a very low loss pass band, but it drops immediately, right? The transition region has to be as flat as possible. That's where we need hybrid. In a millimeter wave systems, we haven't defined the bands for 5G yet, but let's talk about some of the existing systems that we use today, like E-band, for example. The requirement is not that we have to basically drop off immediately. So we can probably get away with a electrical filter where the characteristics demands that you maintain a good performance, but you don't have to be a sharp roll-off. So that way, I believe for those applications, we don't need to go to hybrid. Plus, acoustic filters, the way we use today, won't be usable in millimeter wave. So we have to go to some ceramics filters, right, which can be working at a high operating frequencies. So yes, so unless the bands are defined, it's very difficult to say. But it seems at this point, the roll-off requirement won't be that stringent that you may not require a hybrid filter. But I will basically stop at that point because let's see how the 5G bands are defined.
Okay, another question one of our viewers is asking relates to how much integration across frequency bands you can basically do with a single system on a chip. We've heard that 28 gigahertz and 39 gigahertz seem to be bands of interest. Is it possible to do both those bands in a single system on a chip? Could you even do sub-6 gigahertz?
Very difficult to cover 28 to 39. That's the reason the example that I showed here. Let me go quickly over there to highlight that point. So the special design that has been used here, the wideband Doherty, for the purpose I already mentioned, but not very easy. As you can see, this technology is capable of much more PSAT. So you have to compromise something. So answering your question, probably what will happen is that will be multiple PAs, each optimized towards maximum efficiency and power output. And as you know, right, even 28 gigahertz, we are thinking about at least 800 megahertz of bandwidth. So it's a high bandwidth, by the way. So to cover high bandwidth, which is high PSAT and efficiency, is not a matter of joke. So the reason is we have to probably do multiple PAs and multiple RF components tuned towards these frequencies. But there are always attempt and improvement will be made so that we can do a wider band design to address as much as possible. But yes, at this point, it seems like it will be separately optimized for 28 gigahertz band and around 37, 39. But I'm sure research is going on to make it as wider band as possible.
And probably even if you could do in a single chip a very wide band, as one of our panelists points out, the actual specific array architecture is going to be optimized for one of those bands.
Absolutely. I totally agree with that viewpoint, because it's very important to understand, even though I'm not saying it's a narrow band, but as I mentioned, the antenna spacing, antenna dimension depends on the wavelength. So 28 and 39 is not as widely separated as E band and Ka band, but still they are separated. So there are some inefficiency in the system already built in by covering both the bands, right? So if you want to use the same phase array, it will be highly inefficient at that point. And compared to that, if you do a wider band compromising your other parameters, it will be a very difficult choice. But I won't say that it is not possible, but I will say at that point, depends on your specs, people might try to do that.
So let's explore technologies a little bit here. I mean, you talked in one of your slides about the size of the array depends somewhat on the output power capability of the power amplifier, which ties back obviously to the process technology. And there are some companies that are proposing gallium nitride, for example, for these arrays at mmWave. And one question that we've received asks about beam squint and pulse dispersion across a large array that would limit the instantaneous bandwidth and force someone to go to 3.5 semiconductor technologies for the front end, also to achieve the high effective radiated powers. So what's your sense of the trade-off between some of the silicon technologies and, say, using gallium nitride?
That's an excellent question. Yes, 3.5 compound materials, particularly gallium nitride, is a technology of choice for very high power at very high frequency. It is being used today even in this sub-6 gigahertz infrastructure today. The point here I'm trying to make here is, if you really want to generate very high power for some applications, like for example, macro-based tower, some of the backhaul applications, and if you want to limit the number of elements for that, definitely you have to use a hybrid PA. GaN, gas can be used along with silicon germanium PA there. But when it comes to integration, and you don't have to go off chip, because whenever you want to go to off chip and come back to your chip, you lose signal. Signal integrity is very important in millimeter wave, and it will be much more important in high frequency. Yes, there will be some requirement where you have to go to hybrid for a very high power. GaN will be a technology of choice for that purpose. But for system integration and for any other lower EIRP kind of system with a decent size of arrays, silicon technology, by virtue of the phased array, it can be useful. And at some point, it will give way to silicon germanium. It can do integration or hybrid as well. And beyond at some point, yes, GaN will be used as well.
All right, thank you. Unfortunately, we've run out of time for the webinar, and so we can't take any more questions. I want to thank Anirban Bandyopadhyay for the excellent presentation on the silicon capabilities for 5G millimeter wave phased array systems, and also we appreciate Global Foundries sponsoring the webinar and making the information available. A couple of reminders before we sign off today. Everyone who registered will receive a copy of the presentation. You'll shortly receive an email with a link to download the slides. Also, we've recorded the webinar. It will be available to view on demand. You'll find it in the events section of the Microwave Journal website, and it will be posted within about 24 hours. So you can go to microwavejournal.com, click on events, then webinars, and you will be able to find it. So if you found the presentation informative, please let your colleagues know so they can watch it as well. Thanks, everyone, for joining us today.